Okay, so today we're going to start learning about our second to last unit, simple harmonic motion and sound. So we're going to start with simple harmonic motion. Okay, we call it SHM for short because nobody likes to say simple harmonic motion over and over. It is the repeating back and forth motion like in a pendulum or a spring. Okay, so some properties that you need to know of simple harmonic motion and waves in general. So one is frequency, which is denoted by kind of a fancy looking lowercase f. It's like curled at the end and the top. This is the number of oscillations per second. So think of like if it were a pendulum, right? So pendulum, if it starts in the middle, it swings up one side and to the other side. And so one swing forward and then backward, that's one oscillation, okay? So we say that frequency is equal to the number of cycles, so one oscillation per second. Okay. All right, and then another property of waves in simple harmonic motion is the period. It's denoted by a capital T, which may be confusing and might bring back flashbacks of forces, so I'm so sorry. This is the time for one oscillation. Okay, so frequency and period are related. So frequency equals 1 over the period, but that means also that the period equals 1 over frequency. So these are interchangeable. They're just inverses of each other, basically, where F is your frequency, and that needs to be measured in hertz, and T is your period, and that's measured in seconds. Okay? All right, then we have a couple more properties to talk about. So our third property would be amplitude, which is the magnitude of maximum displacement. So for a pendulum, we think of that as the theta, the angle. So if you bisect a pendulum swing in half, the angle theta it makes with respect to the middle to the highest point, that is the magnitude of maximum displacement for a pendulum. For a spring, it's a little different. For a spring, it's the distance from its equilibrium position, okay? So if you had a spring, think about, let's say I drop something on top of a spring. Maybe I'm pulling it. So here's a ceiling, and here's my spring when it's relaxed, and here's my spring when I've stretched it because I hung something from it that has some mass to it. So that's where it gets stretched. So from here down to here, this is your x. So this is where it is normally when it's resting. This is where it is when it's stretched to its maximum displacement. So x is the distance of your maximum displacement. So that's different for a spring, of course, than it is for a pendulum. Okay, so just noting that. The amplitude actually describes the energy of a wave. And we'll talk more about that next class when we talk about waves and all the different parts of them. All right, so the fourth property would be wavelength. And it's denoted by a lambda, which is a Greek letter. And this is the distance between two successive points on a wave. Okay, all right, so those are the properties, and we'll talk more about wavelength again the next time when we talk about actual waves. All right, so now let's talk a little about pendulums. The period depends on length, which is denoted by a lowercase l, and acceleration due to gravity, which is denoted by a lowercase g. And as you recall, gravity constant on Earth is negative 9.81, but it's not the same on other planets and moons. So if we take our pendulum that we have on Earth to a different planet or a moon, it'll have a different gravity that's affecting it. So that will change the period, how often it swings back and forth, basically, okay? Period does not depend on mass, which is denoted by an m, and the mass is still in kilograms until I tell you otherwise. I don't think I will though. And amplitude, which is its angle. It's still going to swing at the same angle if we take it to a different planet. No matter what mass we put on it, it's still gonna swing at the same angle. It's still gonna and it's still gonna swing for the same amount of time. These don't change it, but if we change planet, if we change the length of the string that it's hanging on, so I don't know if you noticed a pendulum has a string, it's hanging from a string, and change that length, it will change the period. Okay, pendulums have a very specific formula. So T of a pendulum, I'm going to call it TP. Let me see what it looks like on your formula sheet. I don't want to, if it's a little p or a big P. Yes, it's a little p. Okay, so TP equals 2 pi square root L over G, where TP is the period, which is in seconds. L is the length, which is in meters, and G is the acceleration. Almost the bottom of the page there. Acceleration due to gravity, and that's in meters per second squared. Okay, all right, so let's do a little practice. Okay, so here's an example problem. A pendulum swings with a period of 2.16 seconds what is its length? If it doesn't say what planet it's on, let's just assume it's on planet Earth. So I know that TP equals 2 pi square root L over G. I'm looking for L. So I'm going to divide both sides by 2 pi. I'm going to square the other side to get rid of my square root, and then I'm going to multiply by G. So now I have an equation just for L. So since we're on planet Earth, that's 9.81. Don't worry about the negative, just call it 9.81. Magnitude only. The period is 2.16 seconds over, and I would put in my calculator, I would put 2 pi in parentheses on the bottom. Otherwise, you're going to screw it up when you enter it, and you have to be smarter than the equipment you're working with because you're in honors physics. So, oh, and we're squaring that whole section. Okay, so 9.81 times 2.16 divided by 2 pi squared equals. All right, so I get about 1.16, and this is length, so it's meters. Okay, and that's a good example of a pendulum question. All right, so now let's talk about springs. Oops. So for springs, the period depends on mass, which is a little m in the equation, and the spring constant. Which is denoted by a lowercase k. Okay. Period does not depend on amplitude. If I could spell, that'd be awesome. Amplitude, which in this case will be x, and acceleration due to gravity, which is a lowercase g in the equation. Okay, so this one also has an equation that's on your formula sheet, and it's TS equals 2 pi square root m over k. So it's on your formula sheet. You don't have to memorize it. Where T is the period in seconds, m is the mass, and it must be in kilograms. So you need to go between grams and kilograms quite easily at this point in the course. And spring constant is K, and its units are Newton per meter. Okay. Now, earlier in the year when we talked about the energy in a spring, we did Hooke's law. And you're going to have to use Hooke's law sometimes for some of your homework problems. And that's the one where K equals F over X. And this also is in your formula sheet, where F is your force, and that's in newtons. I know, flashbacks, I'm super sorry. And X is your distance from equilibrium position, which is in meters. And again, that one is another one that we like to put in a different unit, and you're going to have to be proficient at converting it to meters often, okay? Okay. All right, so let's do a little example problem. All right. A 15 Newton force stretches a spring 60 centimeters. See, not meters. you attach 800 grams, what's that? That's grams, not kilograms, oops, of mass. What is the period? Okay. So we know that T of a spring is equal to 2 pi square root m over k. But we don't have k, right? We have 15 newtons, which is force. We have 60 centimeters, but we don't like centimeters, right? So we know that x is 0.60 meters, and that's your x value. This is grams, 800 grams. We need it to be in kilograms, so that's going to be 0.800 kilograms, so that's your mass. And we're looking for the period. We can't do this because we don't have K. So first we're going to have to use Hooke's law. So we're going to have to say, okay, so K equals F over X. Well, the F is 15, and the X, because we've converted it, is 0.60. So 15 divided by 0.6 equals 25 newtons per meter. And it's newtons per meter because that's newtons and that's meters. And now we can plug it in right here. So we can say 2 pi times the square root of the mass, which is 0.8 kilograms, right? Over the K value that we just found is 25. And this will give us our period of the spring. So 2 pi times the square root of 0.8 over 25. And so your period is 1.12 seconds. Okay, all right. So that's all your notes for today. So where are these things on your formula sheet? Let's talk about that for a second. So on the front of your formula sheet, we did energy earlier in the year, and there's Hooke's law, F or K equals F over X. So that's right there. And then of course there's G, but don't use the negative because we're just talking in magnitude for our purposes. And if you turn to the back, there's more formulas on the back of the sheet. And so here is the formula for your pendulum, for the period of a pendulum. Here's your formula for the period of a spring. And here's the formula for frequency, okay? So by the time we're done with this unit, we will use basically from this equation, this for the rest of this row, this whole row, this whole row, and this row. So the back is really important. So hopefully you'll get the hang of things pretty quick, okay? So good luck on your homework.